Modern power systems are undergoing a fundamental transformation driven by the rapid integration of inverter-based renewable energy resources, electrification of transportation, and the proliferation of distributed generation. This shift toward inverter-dominated systems has introduced unprecedented operational challenges for transmission and distribution networks, including high ramp rates, reduced system inertia, bidirectional power flow patterns, voltage instability at the distribution level, and frequency volatility at the transmission level. Battery energy storage systems, BESS, have emerged as a critical grid infrastructure asset capable of addressing these multifaceted challenges through fast, dispatchable, and controllable power injection and absorption. Unlike conventional synchronous generation, BESS can react in milliseconds, making it ideally suited for real-time grid balancing and the provision of essential system services. The following analysis examines 6 critical questions that utility engineers, planners, system operators, and regulatory bodies must address to successfully integrate BESS into modern power systems, with particular emphasis on transmission and distribution planning, grid operations, and power system economics. The first fundamental question concerns the role of BESS in addressing distributed energy integration and managing grid load variations in inverter-dominated systems. Contemporary power systems are increasingly characterized by high penetration levels of solar photovoltaic arrays, wind turbines, electric vehicle charging infrastructure, and various forms of distributed generation. These resources introduce significant operational challenges that were not present in traditional synchronous machine-based grids. High ramp rates, rapid changes in power generation over short time periods, can occur when cloud movements affect solar output or when wind conditions change suddenly. This places stress on conventional generation resources that must ramp up or down quickly to maintain system balance. More critically, the reduced system inertia inherent in inverter-based resources means that the grid's ability to resist frequency disturbances is diminished. System inertia, provided traditionally by the rotating mass of synchronous generators, acts as a buffer against frequency changes. When this inertia is reduced, the grid becomes more susceptible to frequency excursions and potential instability. BESS addresses these challenges through multiple technical mechanisms. Time-shifting energy, achieved through peak shaving and valley filling, allows energy to be stored during periods of low demand and discharged during peak demand periods, effectively flattening the load curve and reducing the need for peaking generation capacity. Synthetic inertia and fast frequency response, FFR, capabilities enable BESS to respond to frequency disturbances within milliseconds, providing the grid with the rapid response capabilities needed to maintain frequency stability in low inertia environments. Voltage regulation through reactive power control, QV control, allows BESS to inject or absorb reactive power to maintain voltage levels within acceptable limits, particularly at the distribution level where voltage fluctuations caused by distributed generation can be problematic. Congestion relief without network reinforcement represents another critical BESS function. By storing energy when transmission constraints would otherwise limit power flow and discharging it when constraints are relieved, BESS can defer expensive transmission upgrades and improve overall grid utilization. Finally, islanding and black start support capabilities enable BESS to maintain operation of critical loads during system disturbances and assist in system restoration following blackouts, a capability that becomes increasingly valuable as the grid's resilience requirements become more stringent. The South Australia Hornsdale Power Reserve provides a compelling real-world demonstration of BESS capabilities in addressing these operational challenges. Commissioned in 2017, this 150 megawatts per 193.5 megawatt-hours facility was initially conceived as a response to the South Australian energy crisis of 2016. During which multiple system blackouts highlighted the vulnerability of a grid with high renewable penetration. The Hornsdale facility demonstrated unprecedented performance capabilities, arresting frequency decline within 140 milliseconds of a major disturbance, faster than any conventional generation resource could respond. This rapid response capability directly prevented cascading outages during major transmission faults, demonstrating the critical role that fast-acting storage can play in maintaining system stability. Beyond its technical performance, the facility generated significant economic value, reducing frequency control ancillary services, FCAS, market costs by over 60% in its first year of operation while generating approximately $13 million in revenue. This case study illustrates how properly sized and deployed BESS can simultaneously enhance grid reliability, reduce operational costs, and provide economic returns to investors. The success of Hornsdale has influenced BESS deployment strategies worldwide, demonstrating that storage is not merely a balancing resource but a fundamental grid asset that enables higher renewable penetration while maintaining system reliability. The second critical question addresses optimal site selection and voltage level determination for BESS deployment. BESS siting is not arbitrary. It must be strategically located to solve specific grid problems that align with technical and economic objectives. Engineers must evaluate siting decisions based on the specific grid services that the BESS will provide and the voltage level at which these services can be most effectively delivered. At the transmission level, typically involving voltages between 132 kV and 400 kV, BESS is deployed for system-wide services that affect the bulk power system. These services include frequency regulation, which requires rapid response capabilities to maintain system frequency at 50 or 60 Hz, congestion relief, which involves storing energy during periods of transmission constraint and discharging it when constraints are relaxed, renewable firming, which smooths the variable output of wind and solar resources to make them more dispatchable, and inter-area oscillation damping, which involves injecting or absorbing power to dampen electromechanical oscillations that can threaten system stability. Transmission-level BESS facilities are typically located near renewable pooling stations where multiple renewable resources connect to the grid, at weak interconnections between different transmission regions, or at high-voltage substations with a history of congestion. These locations maximize the BESS's ability to address system-wide challenges and enable the integration of additional renewable capacity without requiring transmission reinforcement. At the distribution level, involving voltages between 11 kV and 33 kV, BESS is deployed for local services that address distribution network challenges. These services include voltage regulation, which maintains voltage levels within acceptable limits for residential and commercial customers, loss reduction, which minimizes energy losses in distribution lines through optimal power flow management, feeder overload mitigation, which prevents distribution feeders from exceeding their thermal limits, and electric vehicle charging support, which manages the impact of growing EV charging loads on distribution infrastructure. Distribution-level BESS facilities are typically located at the end of distribution feeders where voltage drop problems are most pronounced, in urban load pockets where demand is concentrated, or in areas with high rooftop PV penetration where reverse power flow issues can occur. The voltage level selection rule of thumb is relatively straightforward. Fast system services such as frequency regulation and congestion relief are best provided at higher voltage levels where the BESS can quickly inject or absorb large amounts of power, while local power quality issues such as voltage regulation and loss reduction are most effectively addressed at lower voltage levels closer to the affected loads. The UK National Grid's deployment of distribution-level BESS facilities demonstrates the effectiveness of this approach. Projects ranging from 10 megawatts to 40 megawatts at 11/33 kV voltage levels have successfully deferred substation upgrades by 5 to 7 years by managing peak demand and reducing thermal stress on distribution equipment. Perhaps more significantly, these facilities have solved reverse power flow issues caused by high rooftop PV penetration, enabling continued solar deployment while maintaining distribution network reliability. This case study illustrates how properly sited distribution-level BESS can provide substantial value by deferring capital expenditures and enabling distributed energy resource integration. The third question addresses higher-order sizing requirements for transmission and distribution networks, recognizing that BESS sizing is a multidimensional problem that extends beyond simple power, MW, and energy, MWH, specifications. While primary sizing parameters such as power rating, energy capacity, C rate, the ratio of power capacity to energy capacity, round-trip efficiency, and state of charge, SOC, operating window provide the foundation for BESS specification, advanced constraints must also be considered to ensure reliable and economic operation. These advanced constraints include N1 contingency compliance, which requires that the BESS can provide required services even when one component is out of service, short-circuit contribution limits, which ensure that the BESS does not exceed the fault current rating of the connected network, harmonic distortion limits, which require that the BESS's power conversion systems do not introduce unacceptable harmonic content into the grid, degradation-aware dispatch, which optimizes BESS operation. To minimize capacity fade over time, and seasonal load variation, which accounts for the fact that BESS requirements may vary significantly between summer and winter months. Different applications require different sizing strategies. Peak shaving applications typically require 2 to 4 hours of energy capacity, as the BESS must discharge for sufficient duration to shift load from peak to off-peak periods. Renewable firming applications require 4 to 8 hours of energy capacity, as the BESS must smooth variable output over longer time frames to provide dispatchable power. Frequency response applications require relatively low energy capacity, typically 15 to 30 minutes, since the response is brief but requires high power output. Black start applications require high power output but relatively low energy capacity, as the BESS must provide sufficient power to restart generation resources but does not need to operate for extended periods. The California Independent System Operator, CAISO, experience provides valuable lessons on the importance of proper BESS sizing. Several 100 megawatts per 400 megawatt hours projects initially underperformed due to underestimated degradation rates. The original sizing models assumed conservative degradation patterns, but actual operation revealed more rapid capacity fade, particularly during high temperature periods and when operating at extreme states of charge. This degradation led to reduced availability and performance, undermining the economic case for these projects. In response, CAISO and project developers revised their sizing models to include lifetime energy throughput constraints, which explicitly account for the total amount of energy that can be cycled through the BESS before end of life is reached. These revised models now use more aggressive degradation assumptions and incorporate operational strategies such as limiting the SOC operating window and reducing cycle depth during periods of high temperature stress. The California experience demonstrates that poor degradation modeling can lead to both financial and operational failure. Projects that appear economically viable based on simplified sizing models may fail to meet performance targets and may require premature repowering or replacement. This lesson has influenced BESS sizing practices worldwide, with operators increasingly requiring detailed degradation models that account for operating conditions, cycle patterns, and environmental factors. The improved understanding of degradation mechanisms has also led to the development of more sophisticated battery management systems that can dynamically adjust operating parameters to optimize lifetime performance while meeting operational requirements. The fourth question concerns deployment roadmap development for BESS, recognizing that successful implementation requires a structured approach that aligns grid needs, technology maturity, and market design. An engineering-driven roadmap typically progresses through 3 phases. Phase 1, the pilot and validation phase, involves small-scale projects of 5 to 20 megawatts that are deployed to validate protection schemes, test energy management system, EMS, and supervisory control and data acquisition, SCADA, integration, and demonstrate operational performance under real-world conditions. These pilot projects provide valuable lessons about technical performance, operational procedures, and economic value that can inform subsequent deployments. Phase 2, the grid services expansion phase, involves scaling up BESS deployment to provide multiple grid services including frequency regulation, voltage support, and congestion management. During this phase, operators develop standardized procedures for BESS operation, refine control algorithms, and optimize the economic value through multi-service stacking. Phase 3, the system-wide asset phase, involves deploying BESS at GW scale as a core grid asset capable of providing capacity replacement, black start services, and renewable capacity firming. By this phase, BESS is fully integrated into system planning and operation, with standardized interconnection models, well-defined operational procedures, and mature market mechanisms. Key engineering inputs that must be addressed throughout the roadmap include grid code amendments that recognize BESS capabilities and define technical requirements, standardized interconnection models that streamline the connection process, cybersecurity measures that ensure the secure operation of BESS control systems, and EMS interoperability standards that enable seamless communication between BESS controllers and grid control systems. China State Grid provides a compelling example of a successful BESS deployment roadmap. Beginning in 2016 to 2018, the utility deployed pilot BESS projects to test technical capabilities and develop operational expertise. These early projects focused on frequency regulation and peak shaving, providing valuable data about performance characteristics and economic value. Building on the lessons learned, China State Grid developed standardized control architectures and specifications that were applied across multiple regions. These standards addressed technical requirements, communication protocols, and safety procedures, creating a foundation for rapid scaling. By 2023, China had achieved GW-level BESS deployment, with storage systems playing an integral role in grid operations across the country. The success of this roadmap was enabled by strong government support, clear regulatory frameworks, and substantial investment in research and development. The Chinese experience demonstrates that a structured, phased approach to BESS deployment can successfully transition from small-scale pilots to system-wide assets, provided that there is strong coordination between engineering, operational, and regulatory stakeholders. The lessons from China are being applied worldwide as utilities develop their own BESS deployment strategies, with many recognizing that the phased approach provides a risk-managed pathway to large-scale storage integration. The fifth question addresses procurement models for BESS, comparing centralized utility ownership with public-private partnership, PPP, or independent power producer, IPP, models. The choice of procurement model has significant engineering implications because it directly impacts asset control, dispatch authority, maintenance responsibility, and performance guarantees. Centralized utility ownership provides full operational control and enables tight integration with the utility's EMS systems. This integration facilitates coordination with other grid assets and reduces the risk of operational conflicts. Under centralized ownership, the utility assumes performance risk, degradation risk, and maintenance responsibility, providing complete control over asset operation but also bearing full responsibility for asset performance. In contrast, the PPP/IPP model involves the utility defining technical specifications while a private partner designs, builds, and operates the BESS facility. Payments are typically linked to availability and performance metrics, providing strong incentives for the private partner to maintain asset performance. Under this model, performance risk is allocated to the private partner, degradation risk is shared between the utility and the private partner, dispatch authority remains with the utility, and maintenance responsibility is typically allocated to the private partner. The choice between procurement models depends on multiple factors including the utility's strategic objectives, risk tolerance, capital availability, and regulatory environment. India's Solar Energy Corporation of India, SECI, BESS tenders illustrate the PPP model in practice. SECI conducted competitive tenders for BESS projects with 25-year availability guarantees, specifying performance requirements, technical standards, and payment mechanisms. The tenders include penalties for state-of-charge non-compliance, providing strong incentives for operators to maintain BESS in proper operating condition. Importantly, the grid operator retains dispatch rights, ensuring that BESS operation is coordinated with other grid assets and can be called upon for system needs. The SECI tenders have attracted substantial private investment in BESS, with projects ranging from 100 megawatts to 500 megawatts being developed by international battery manufacturers and project developers. The success of this PPP model demonstrates that well-structured tenders can attract private capital while maintaining grid operator control and ensuring technical performance. Key to this success has been clear technical specifications, robust performance guarantees, and transparent payment mechanisms that align the interests of private developers with grid reliability requirements. The Indian experience is being closely watched by utilities worldwide as they consider similar PPP models for BESS procurement, recognizing that the model can accelerate deployment while maintaining grid operational control. The sixth question addresses policy and regulatory frameworks for BESS, recognizing that effective policy must acknowledge BESS as neither purely generation nor load but rather as a multi-service grid asset with unique characteristics. Key regulatory elements that must be addressed include clear interconnection standards that define technical requirements for BESS connection to the grid. Standards such as IEEE 1547 and IEC 62933 provide important technical guidance but must be adapted to local grid conditions and operational practices. Market access for ancillary services is equally critical, as BESS must be able to participate in energy markets, capacity markets, and ancillary services markets to capture the full value of its capabilities. Defined ownership models are necessary to clarify whether utilities, independent power producers, or other entities can own BESS and what operational rights and responsibilities accompany ownership. Safety and fire suppression codes must address the unique characteristics of large-scale battery systems, including thermal runaway risk, electrolyte leakage, and emergency response procedures. Without adequate regulatory frameworks, several operational challenges emerge that can undermine BESS deployment and operation. Double charging of grid fees can occur when BESS is charged as if it were a load and discharged as if it were generation, resulting in multiple fees for a single operation. No revenue stacking can occur when regulatory frameworks prevent BESS from simultaneously participating in multiple markets, reducing economic value. Dispatch conflicts can arise when multiple BESS owners attempt to provide conflicting services, potentially jeopardizing system reliability. Underutilized assets can result when regulatory uncertainty or inadequate market design prevents BESS from operating at its full potential. FERC Order 841 in the United States provides a landmark example of regulatory action that enabled BESS deployment. Issued in 2018, this order required all regional transmission organizations, RTOs, and independent system operators, ISOs, to remove barriers to BESS participation in wholesale markets. The order recognized BESS as a unique resource that can participate in multiple market types and mandated the development of participation models that enable BESS to capture its full value. The impact of this order has been substantial, with RTOs and ISOs developing tariff provisions that allow BESS to participate in energy, capacity, and ancillary services markets, often with provisions for revenue stacking across multiple services. The result has been exponential growth in grid-scale storage deployment, with the United States becoming a leading market for BESS projects. The success of FERC Order 841 demonstrates that regulatory clarity can unlock BESS deployment by providing market certainty and enabling BESS to capture the economic value of its capabilities. Other jurisdictions are developing similar frameworks, recognizing that appropriate regulatory design is essential for achieving the full potential of BESS as a grid asset. In conclusion, the successful integration of BESS into modern power systems requires addressing 6 critical questions that span technical, economic, and regulatory domains. BESS has evolved from an optional balancing resource to a core grid asset that enables high renewable penetration while maintaining system reliability. Correct siting, sizing, and voltage selection determine project success. Poor decisions in these areas can lead to underperformance, economic losses, and reduced grid reliability. Degradation modeling is particularly critical, as poor assumptions can cause both financial and operational failure, as demonstrated by the California experience. Deployment roadmaps must align grid physics with market economics, recognizing that technical requirements and market mechanisms must evolve together to enable optimal BESS operation. Procurement models directly affect operational flexibility, Centralized ownership provides tight integration with utility systems, while PPP models can accelerate deployment but require careful design to maintain grid control. Regulatory clarity is essential for unlocking full BESS value, as demonstrated by the success of FERC Order 841. The global experience with BESS deployment, from the pioneering Hornsdale project in South Australia to the GW-scale deployments in China and the PPP models in India, provides valuable lessons for utilities, planners, and regulators worldwide. As the energy transition accelerates and renewable penetration increases, BESS will play an increasingly critical role in maintaining grid reliability, enabling decarbonization, and ensuring that power systems can meet the challenges of the 21st century.